Hi everyone, I'm Rohit Kumar Singh, TA for this course, Experimental Physics 2, and this is the third live session of this semester. So, this course is being taught by Professor Aman Kumar Das of IIT Kharagpur at NPTEL. In today's live session, I'll basically recap some of the concepts of optics, such as uh, topics related to lenses and mirrors, uh, and then I'll solve some sample problems to show you how to deal with the exercises. And so, if you have any doubt at any point, please feel free to ask. Okay, so let's start. Uh, so, what is refraction? Hmm, Okay. Yeah. So refraction is a phenomenon uh, which involves change in the path of light. With and When does it happen? So it happens when light passes through one medium to another, and both the mediums should have different refractive index. So suppose there is a glass slab and a ray of light is coming. So what will happen is that it will bend uh, in either left or right, which will depend on the refractive index of both the materials. So since here the light is the refractive index of this glass is higher than the light that of the air, so it will bend towards the normal direction. So these things you must have studied in your uh, class 12th physics. So just to remind you, uh, and so there's a simple formula, Snell's law, and so suppose let me draw it more clearly. So, so this is the incident light. It will make an angle I with the normal, and then this is the refracted light. Let's suppose this angle is R, which it make with the normal N. And the Snell's law simply says that the sine of incident angle, the ratio of sine of incident angle and sine of refracted angle is uh, the constant, which is denoted as A mu B. So this is what we called relative refractive index. And so suppose if the air has a refractive index 1, then this will be just the refractive index of uh, the glass. So mu G, let's say. So this is the Snell's law. And so the lenses, all the lenses that we have, uh, like convex and concave lenses and other combination of different radius of curvature. Uh, so the basic principle is this refraction of light, okay? And so yeah, let's get to the some of the main formula of lenses. I'll not derive all the formula because that are being done in the lectures. So I'll just write out the formula and yeah, uh, maybe if you have some confusion, you can ask, or otherwise, I'll just write out the formula and I'll go on to solve some problems. Okay, so now the first formula that that's I think the most important one is what we call the lens maker formula. So, yeah, but first uh, let me get you familiar with some notations. So suppose this is a convex lens. So it will be having two radius of curvature R1 and R2. Uh, so you can complete this side into a circle and then this side also into a circle, and this will be your R1 and this will be your R2. So ideally these R1 and R2 will be same, but sometime we'd like to change them to make a different type of lens. So yeah, and then this is our the middle point is what we called our pole, or you can also call it optical center. So yeah, then we have focal points. So what is a focal point? From like for the mirrors, the focal point is where all the light coming from the infinity converge. So here too, suppose these are parallel lights coming from infinity, and they will converge by this converging lens to a point, and this distance from the optical axis is what will optical center. It's what we called our focal length, and this point is our focal point. Okay, so yeah, these things are very basics. If you have any doubt, you can ask. Um, so with this, I'll like to write out first the lens maker formula, and then yeah, then I'll write some of the other important formulas. Okay, so so the lens maker. So this distance focal length is denoted by f small f, and the lens maker formula is simply 1 by f equal to suppose this lens has a refractive index n, uh, so then n minus 1 and the two radius of curvatures, if they are equal, then we can put R1 equal to R2 in this formula, but in general, let's keep it like this. Okay, so this is the lens maker formula. Okay, now one more important formula that we have here is the thin lens formula. Uh, so for the so we can get the thin lens formula from here, and to do this, so yeah, it's a simple derivation. So uh, I'll not I'll not do that. This derivation is, I think, in the lecture, so you can go over it. So the thin lens formula, which we can derive in principle from the lens maker formula, is simply 1 by v minus 1 by u equal to 1 by f. And so here u is the uh, object distance, and v is the image distance from the optical center. Okay, so and f is the our focal length. Yeah, so this is a very important formula, and other than this, so suppose you have sometimes you have two lenses stacked after each other. Okay, and so for this type of lens combination, we would like to know the effective focal length. And so suppose these rays from infinity are coming, so these two lenses will behave as a single lens, and they will converge the light at some point, and this focal point will be a combination of what we get from these two lenses separately. So it's simple derivation. Maybe I'll just uh, do this. So this thin lens formula we have, and so from the first lens, there will some the v1. There will be some v1 because suppose the image distance is v1, and the u object distance is here infinity, but let's write it u to get a general formula. And then we have the first focal length, and then for the second lens, uh, here the the image distance will be, suppose v, whatever the image that it's forming. So suppose here at the focal point, and here the object distance will be from the first lens, so it will be v1 and the focal length f2. Now if you add these two equations, uh, what will happen is this get cancelled with this v1, and you will just have 1 by v minus 1 by u equal to 1 by f1 plus 1 by f2. Okay, so and this you can write as 1 by f effective. So you get the formula, so the thin lens formula equal to 1 by f effective. So what does it say is that this combination of lenses is equivalent to having a single lens with focal length f effective given by the simple sum of inverse of the two focal length. Okay, so yeah, this is also one important formula. Then uh, yeah, then the thing about power. So power of lens is power of a lens is defined as inverse of focal length. So how powerful a lens is defined as how closer it can focus. Okay, so 1 by f, and power for different combination of lenses, like here p effective, we can write it like p1, p2, and so on. Okay, because just here you can put uh, 1 by f effective as your p effective, and 1 by f1 equal to p1. So this formula is given by that. Okay, then you have then there is a formula for magnification, and magnification is so magnification is called, so whatever your me so okay, let me erase something. I have no space here to write, so yeah, let me erase this part. uh, Sorry. Yeah, so I'll write this one here. 1 by f effective equal to 1 by f1 plus 1 by f2, and I'll erase this one. Okay. Okay, and so the magnification is defined as the, so suppose there is a lens. Okay, and you have an object here, and so this lens will produce some image of this object here. Okay, and so this is the height, so this is suppose h1, and this is h2. So magnification is simply h2 minus h2 by h1, and this you can calculate. It is just the ratio of image distance and object distance. Okay, minus v by u, and this minus is due to the convention that we take we take the distance along the incident ray, as positive and opposite to that as negative. Okay, so yeah. So this will depend on either your uh, image is real or virtual. So suppose if this image is formed on the left side, this minus sign will be gone. I mean, if the image is real, this is what you have. If the image is virtual, your magnification will be simply V by U. So it is just a convention, okay? So for convex lens, this is true. For real image, for virtual image, convex lens. Okay. Now, if you have a convex lens, concave lens, they always form virtual images. So your magnification is just h2 by h1 equal to v by u. Okay. So yeah, that's it. I think, and yeah, the unit of power is diopter. Okay, it's just, and where this frequency is in sorry, this wavelength is in meter. When the wavelength is in meter, so suppose the focal length is 1 meter, then your power is 1 diopter. Okay. Yeah, that's it. That's all the concept you need for today. And if something new come up, I'll try to explain it as well. Okay. So with this, let's move on to our problems for today. So yeah. Let me. Okay. So the first problem that I have today here is this, and it's a very easy one. So I just showed. So let me read the question. So the question is: a beam of parallel rays is brought to a focus by a thin convex lens of focal length f. Okay. So what does it say? So there are some parallel rays coming like this, and it's brought to a focus by a thin convex lens. Okay, it is being focused. So this is the principal axis. Focus. Okay, and its focal length is given as f. Now, a thin concave lens of same focal length is joined to the first lens. So this was our first convex lens, and then it is joined by a concave lens. So concave lens is something like this. Okay. Now, and this the focal length for this concave lens is also f. So now it's asking what will happen. So yeah, I mean ideally I mean, it's intuitively you can also answer this question because this is the so convex lens is what does it do? So it converts the parallel rays to a point, and a concave lens, what does it do? It diverges the rays. Okay, so if you combine a concave and convex lens, it the ideal thing it should do is nullify the effect, right, of each other. Intuitively you can guess this, and to see this you can use the formula that I just showed you. So F effective 1 by F effective is given by 1 by F1 plus 1 by F2 if you have two lens combination, and here both F1 and F2 are F, but so the focal length for concave lens is here, and the focal length for concave lens, oh sorry, focal length for convex lens is here, and focal length for concave lens is here, and the beam direction is this. So F1 will be F, okay, but F2 will be minus F. So what if you put that here, your F effective will be 0, 1 by F effective will be 0, and your F effective will be infinity, right? So what does it mean is that, so this combination of lenses will have a focal length at infinity. So having a focal length at infinity means the parallel rays will just pass through parallelly, and they will keep on going parallelly up until infinity. So yeah, I mean, we guessed it right. The combination of these two lenses nullify the effect of each other, and uh, it doesn't. I mean, it will have no effect on the parallel rays, and parallel rays will continue as before, uh, parallelly up until infinity. Okay, so yeah, it's a very simple question. uh, let's move on to the next one. Now here what we have, so a biconvex lens. Biconvex lens is simply uh, a lens which has both the side convex, uh, I mean the curvature is both round curvature. So the biconvex lens of refractive index 1.5. So here refractive index is 1.5 given, and for both R1 and R2, it has radius of curvature R1 and R2 20 centimeter. Okay, so which one of the following option describe best the image formed of of an object of height 2 centimeters? So the H1 is given, okay, and it's placed 30 centimeter from the lens. So 30 centimeter from the lens. Uh, so 30 centimeter left or right, it's not mentioned. Uh, So let's assume that it is kept in the left. Okay, so this is the h1 and this is our u, which is minus 30 centimeter, right? Now we have, so now what is asked, image formed. Okay, so we have to calculate what is the image form, uh, I mean what image could be formed from this lens. But for that we need to know the focal length of this uh, convex lens, by convex lens, right? So how do we do that? So to calculate the focal length from these information given, we need the lens maker formula that I wrote here. Here, this lens maker formula we need. Okay, we are given the refractive index, we are given the R1 and R2, so we can calculate the focal length of this biconvex lens, right? So let's do that. So 1 by f is just n minus 1, 1 by r1 plus 1 by r2. So n is 1.5 minus 1. R1 R2 are both 20 centimeter. So we can just write 1 by 20 plus 20. Okay, and so this will be 0.5 into 20. So this is just 2 by 20, which is 1 by 10. And so the focal length is 0.05 centimeter, right? Sorry, 1 by f is 0.05 centimeter. And if you invert it, focal length will be 1 by 0.05, 100 by 5, it's just 20 centimeter. Okay, so we have calculated the focal length. Now we can use the thin lens formula, so which is 1 by v minus 1 by u equal to 1 by f to get the image distance. And so we can, and you have this information that u is minus 30, so 1 by v, so just separate this calculation. Okay, 1 by v, so minus minus plus 1 by 30 equal to 1 by f, which is 20. And if you calculate this, so 1 by v equal to 1 by 20 minus 1 by 30, 60. 3 minus 2, 1 by 60. Have I done something wrong? Mm, no. Okay, good. Yeah, so V is 60 centimeter, right? Now, so this is the V. Now what we can do, so the image will be formed on the right side because we have got a positive V. So somewhere here, so the light will come, it will form my image somewhere here. Now we can calculate the height using the magnification formula. So as I told you, h1 by h2 equal to v by u minus v by u, and because for the real image we have the minus sign, and then you can we have the h1, which is 2 centimeter. So h2, the image height, we can calculate, and v by u minus v by u will be 60 minus minus plus 30 equal to 2, right? So h2 will be what, 4 centimeter, correct? So uh, the answer will be real, and real images are always inverted. So inverted, and height is 4 centimeters. So the D will be the correct answer. Okay. Yeah, and here I forgot to tick the correct answer. Here the focus point shifts to infinity is the correct answer. Okay, fine. So this is also a easy problem. You have to use three formula here: the lens maker formula, the thin lens formula, and the magnification formula. Okay, so this one is the magnification formula. Okay, now the third problem. So here what we have, let's see. Sorry. Here we have the question: a convex lens of focal length 30 centimeter produces 5 times magnified real image of an object. Okay, so that is the information here. Is a convex lens. Okay, its focal length is 30 centimeter, and the magnification is 5, so it produces 5 times magnified real image of an object. Now we are asked what is the object distance. Okay, so some object is here, we have to calculate the u. Okay, and the information that we have is we know the f, and we know the magnification, which is 5. Okay, so uh, first let's, yeah, so from the magnification what we can do is just write out the formula. So h1 by h2 equal to minus v by u is equal to 5. Okay, here we know that uh, sorry, here we know that uh, so we don't know we don't know u. Okay, and we only know yeah, and we have this relation between v and u, which is v is minus 5 times u. Okay, so this is the one equation that we get from here, correct? No, but oh, okay, and one more thing is that uh, so V should come out positive because U is anyway negative. So yeah, that will be that we can put it here because U is the image distance. It should it's negative, right? So we can change the sign here and just write V equal to 5U. Okay, because as I wrote out here, for real image, uh, how did it go? Okay, h2 minus h1 is equal to v by u. Okay, yeah, for the real image we had this minus sign, remember? So yeah, and I think I changed the sign. So h2 is our image distance and h1 is our object distance. Okay, yeah, so first, so we have this relation, and now we can use the thin lens formula, which is 1 by v minus 1 by u equal to focal length, which is given as 30 centimeter, right? Now uh, so 1 by v we can write 5u, and because the object distance is negative we can change the sign, and 30 we'll have here. So from this, let's calculate the u because only u is unknown here, and we have this equation. So 5u 1 plus 5 equal to 1 by 30, and u will be simply 6 times 30 by 5, right? 5 6 30, 36 centimeter. Okay, so this is the object distance, this distance 36 centimeter. Okay, so yeah, this way we can calculate. So option A is correct. This is also a very simple problem. It just needed the thin lens formula and magnification formula. The sign conventions can get confusing sometimes. So yeah, I mean, just remember that on the left side, if you're going on the left, if you're measuring distance on the left side, it will be negative. If you're measuring distance towards right, towards the beam, it's positive. Okay, so this way you will not do some wrong calculations. Okay, good. So now, yeah, this one is fine. Let's move on to our next problem. Okay, here the problem is a plano convex lens. Oh, sorry. Yeah, a plano convex lens is made up of refractive index 1.5 and the radius of curvature of its curved face is 25 centimeter. And then asked is what is the power of the lens? Okay, now plano concave lens will be something like this. So this side will be plane and this other side will be concave. Okay, so this is a plano convex lens, and this is the principal axis. Its refractive index is 1.5, and the radius of curvature of this curved surface here, this one, is given as 25 centimeter. So what will the radius of curvature of this plane surface? It will be just simply infinity, right? Because it doesn't curve. So yeah, we can take it as infinity. And we are asked what is the power of this lens? How well it can converge? So, as I told you, power is just inverse of focal length in meter. Then you will have the unit as diopter. So in principle, we have to just calculate the focal length of. Hmm, what sorry. Yeah, think, okay, diopter. So we have to calculate focal length of this lens. Okay, and how we can do this? So for focal length, if you are given refractive index and radius of curvature, we can use the lens maker formula simply, which is 1 by f equal to n minus 1, 1 by r1 plus 1 by r2, right? And 1 by r1. So here, as I mentioned, r1 is infinity. So 1 by r1, 1 by infinity is just 0. So you have n is 1.5 minus 1, 0 plus 1 by 25 centimeter. Okay. So 1 by f is equal to 0.5 into 1 by 25. So let's write it as 0.25 meter. Okay, because we need the answer in meter. So just invert these and we'll be having our focal length has 0.25 divided by 0.5. Okay, can write it like this, 5. So it's simply 0.5 meter. Okay, this is the focal length, and so power is simply 1 by 0.5 meter, which will be just 2 diameter, right? So this is also a very simple question. So yeah, this lens, uh, this lens will have a power of 2 diameter. Okay. Now, yeah, the lens maker formula is really helpful in solving these types of problems. Uh, so here's one application of that. Now let's get to next problem, which is a lens immersed in a transparent liquid is not visible. Under what condition can this happen? So yeah, this is a simple question. This is interesting. So you suppose you have a pool of water, okay, and you can place a lens inside it, and it will be completely invisible. Okay, now what should be the refractive index of this lens in order to have this condition? Uh, yeah, you can guess, it's simple. It should have the same refractive index as the water, as the liquid, whatever liquid you have. How? So I showed you, suppose this is the liquid medium, okay, and this is the lens medium here. So whenever something is visible, uh, it whenever something is visible, it means that either it is reflecting some light, or either it's yeah, I mean, something is visible through reflection only. Okay, and if the lens and liquid has the same refractive index, okay, so what will happen is the light ray will simply pass through it undeviated. Okay, and because from the Snell's law you have this, and this mu2 by mu1, they are same, so they will cancel. So sine I equal to sine r, I equal to r. So there is no change in the path of the light, and so this lens will be completely invisible. Okay. Yes, yeah, so this is a very simple problem, simple thing. You can think about it. Yeah. Okay, now Please give me a minute. Something wrong with the pencil. Sorry. I think it's working now. Yeah. Okay. So, okay, this is also a simple problem. Let's get to another next problem. Here it is, the question is, in the case of a concave mirror, the image of an object is. So now here question from a mirror. So concave mirror is like, so this is, concave mirror is when the inner side is silvered and you have this other side as your reflective surface. So suppose the light is coming from the right, it will get diverged like this. Okay. Oh, sorry. No. This is a convex mirror, right? Concave mirror is opposite. Sorry. So so to remember this, just remember this cave here. So cave is something which is, uh, so this is like a cave thing, right? Something is, uh, whatever there is inside. So yeah, this is the reflective surface, and it converges all the light point, which is the focus. Okay, so so in the case of concave mirror, let me draw it properly here. As you can see, suppose these are the parallel rays. Okay, and suppose here is your focal length. All these rays will be converged at this point. Okay, this is the pole of the mirror. This is the silvered side. Okay, so the answer will and so and this image, so suppose, so let's take an example. Okay. uh, so suppose here this is your concave mirror. Okay, there is an object here, a b, so and this is your silhouette side now. So it's the one ray from here will go like this parallelly, and it will pass through the focal length like this. Okay, and one more ray might one more ray uh, which will be like this, suppose, and suppose it pass through it center of curvature C. Okay, because we need two rays to make an image, and when you extrapolate these in this direction, they will meet somewhere, and there will you will have your image, right? So, and this image, because it's inside the mirror, it is always virtual, right? You cannot uh, project it on a screen. It's always virtual, and it will be magnified, as you can see here, and it will not be inverted, it will be erect. Okay, so option C is true here, right? So yeah, always for concave mirror this thing happens. So if you want to magnify something, you will have to have a concave mirror if you want to magnify some image. Okay, so yeah, so you can see this in using a spoon. So the spoon has from the concave side you can see this. If you'll see, your face will be elongated, and it will be straight. So yeah, that way you can think about it. Now, that's it for this problem. Let's get to our next problem. Here we have, so the question is, which of the following can make a parallel beam of light when light from a point source is incident on it? Okay. Uh, so the question is, suppose some parallel beam of light is coming. Oh, sorry. Yeah. So we want to have a parallel beam of light. Okay. And the source is, suppose, a point source which is emitting light in all the direction. So let me write more clearly. So you have the point source which is emitting light in all direction, right? So these are the all the rays in all the direction. Okay. Now you want to have a parallel beam of light. So what mirror or lens you can use? So yeah, it's simple. So if you will use, uh, let's say, a concave mirror. So first let's use a convex mirror. So convex mirror is this, right? This is your silvered side. So these rays after getting, so this will go like this will go like this. So it will not be parallel, right? They will not be parallel after reflective, reflecting. So you cannot have a convex mirror. So this option is not good. So this option is not true. Now, okay. Now we put a convex mirror. Sorry, concave mirror. This one is not true. Now this one, if you have a period, so if this point source is located at its focal length, these rays after reflecting from it will be straight like this. So these will go parallelly. Okay, and so yeah, then concave mirror will do the thing. Okay, now so the concave mirror is true. So here you have concave mirror, here you have concave mirror. But can which lens can do this same thing? So to see that, so suppose these are the rays going. So if you have a concave lens, so concave lens is like this. It will again, so light will uh, of, inside of it, light will be like this. It will be like, so it will diverge the lens. So convex lens always diverge the, sorry, concave lens always diverge the light. So it's not good. So this option mm, is not true. So if you have a convex lens, this might do your work of making the rays parallel because it converges the. So if your point source is at the principal focal point of this convex lens, it will make the immediate light parallel after passing through it. So yeah, option A is correct. Okay, this is also a simple problem. There's one option C, which says that let's keep two plane mirrors. So these are the light emitting from the point source like this in all direction. So it's saying let's keep two plane mirrors 90-degree to each other. So like this and this. So what do you think will happen? So yeah, it will it will not make it parallel. So suppose one ray will reflected from here, it will go here, it will be here. Here it will go here, then maybe here, like this. But in principle, they will not be parallel after um, coming out. So you can try this at your home with some leisure. You can try. take two mirrors, place 90 degrees to each other, and take two lasers. Uh, Try if you're able to get this. Okay. I mean, you can make a calculation, but you can make a calculation also. Here you'll get the same answer. Yeah, but it's interesting. Okay, so now the eighth problem that we have here. Uh, so what does it say? A 5 centimeter long pin. Okay, so we have a object which is 5 centimeter height of object. H1 is 5 centimeter, and a 2.5 centimeter long image of this object is formed. So the object height has been diminished and it has formed at 36 centimeter in front of the mirror. Okay, so V is, so what will be right, minus or plus? So in front of the mirror, that means, so suppose here is your concave mirror, okay, and here was your object H1, and the what wherever the object the image has formed, it's diminished in size H2, and this distance is 30 centimeter. So because since it's in the so the distance is in the opposite direction of the incident beam, the V will be minus 30 centimeter. Okay, from the convention, and the magnification is H1 by H2. Oh, sorry, H2 by H1, always image by object, equal to minus V by U, okay, or minus 2.5. So since so this H1 is sorry, and the image of this, yeah, one more thing, uh, because this is a concave mirror, the image will always be inverted. I forgot to mention that, right? Real images are inverted, so the image will be like this, H2. So this will be negative. The H2 is minus 2.5 and this is 5, right? And then you have minus 30 by U. Now if you calculate this, minus 1 by 2 equal to 30 by U. So U is 15, minus 15 centimeter. Oh, sorry. No, 60. So U will be minus 60 centimeter. Okay. So the image will form at 60 centimeter here, somewhere here. Okay. Not here. So image is somewhere here, H2 at 60 centimeter. Okay, good. Now the main problem here is to find the focal length. So now it's easy. We can use the thin lens formula 1 by v minus 1 by u equal to 1 by f. Okay. 1 by v is minus 30. So u is minus 60. So minus minus plus 60 by 1 by f. Here 60 minus 2 plus 1 equal to 1 by f. F will be simply, oh wait, mm, minus, okay, yeah, sorry, this will be minus minus plus, right? 3 by 60, so 20, yeah, 20 centimeter. So this will be the focal length of the this concave mirror. Okay. Now, next problem. Uh, yeah. So the next problem here is, which of the following statement is true? A convex lens has 4 diopter power having a focal length 0.5 meter. A convex lens has minus 4 diopter power having a focal length of 0.525 meter. Then 4 diopter having a focal length of, so concave lens has 4 diopter power having a focal length of 0.25 meter, or all options are wrong. No. First thing is so since the focal length is positive, right? So I mean the focal length is positive and we know the formula for power is just 1 by f. So this cannot be true. It cannot have negative power. So and yeah, and since the focal length is positive, it indicates that the it is a convex lens, because as you might remember, the convex lens has focal length, principal focal point this side, and it's always positive, right? So yeah, I mean the positive focal length means uh, that basically this is a convex lens, and if you can calculate the power 0.25 meter, it's 4 diopter. So it's a convex lens and it's having a 4 diopter power. Okay, so option A is correct here. Okay, this so far so good. Now our 10th problem. So it is also a qualitative problem. The question is, magnification produced by a rear view mirror fitted in vehicles is option A less than 1, option B more than 1, is equal to 1. It depends upon the position of object in front of it. Okay, so you know that there are rear view mirrors towards the side of front seats, okay, which is used to monitor the vehicles that are coming from behind. And have you ever noticed what you can see from in those mirrors? So these mirrors are always convex mirrors. Okay, so we use convex mirrors in these rear view mirrors, and sorry, mm, convex mirrors, as you know that. So if this is the height of an object, convex mirror, since it converges the light, it will always produce a diminished image. Okay, uh, and the image, uh, yeah. So you can say the h2 by h1 will always be greater than 1. Okay, because sorry, h2, it's always be less than 1. Sorry, because h2 will be always lesser than h1. Okay, so the correct answer here is a, less than 1. Okay, so that's why you might find a text written in those mirrors that object in the mirror is are uh, closer than they appear. So because since they are smaller, you might think that they are far, but that's not the case because the object size has been diminished. That's why you get this false idea that they are far, but they are not really. Oh, sorry. It's not. Sorry, it's not a mm, lens. It's mirror. But yeah, same thing is there. Same concept is there. So this is sorry. This is not a convex mirror. Convex mirrors. So yeah. Sorry. This is a convex mirror. Okay. Uh, so yeah. Suppose this is the height of the object. Light will come here, it will be reflected like this, and the virtual image will be produced somewhere here, and which will have uh, h2, and it will be dimmed. So same thing is happening here also. Light is getting converged, so the height of the images will be smaller than the height of the object. Okay, so, yeah. Silly mistake. So let's go to our next problem. Here the question is, Rays from sun converge at a point 10 centimeter in front of a concave mirror. Okay, so yeah, this is maybe a long problem. So rays from the sun will be parallel because let's assume it's coming from infinity. You have a concave mirror like this, and they converge at a point. So this is the principal axis, let's say here, and so this will be 10 centimeter. And so yeah, this 10 centimeter is uh, in general the focal length. It will be negative because it's measured in opposite direction of incident beam. Okay, so and the question is, where should an object be placed so that the size of its image is equal to the size of the object? So we want to have h1 equal to h2. Okay, and so to have this, we should have u equal to v, right? Because m is h2 by h1 equal to v by u. So yeah, so if h1 and h2 are equal, that means v and u should be also equal. And so when can this be happen? When can this happen? So let's so suppose this is your focal length. Suppose here is a point. Okay, if you put your object at some point here, uh, light will go from here, and suppose one light which will be parallel will cross from the focal length. Okay, suppose another light is crossing from suppose wait, this is the this is the center of curvature, and one ray might pass through it like this. Okay, and you extrapolate it here, they will meet, you will have your image, right? But but this image will always be larger than this uh, object here. Okay, now let's take another condition. So this is a concave mirror. So now here what you do is you keep your image in between the center of curvature and focal length, focal focus. Okay, so again you have object, parallel rays will pass through focal point, one ray will pass through the center of curvature. Okay, and they will never meet, rather. So you will have to extrapolate this way, and you will again have a larger object, but it will be a virtual image. Sorry, larger image, but it will be virtual. Okay. Then you can have the third case in which, sorry, uh, I'm running out of space. Let me remove these things. So yeah, now let's take the third case, okay, where you will put your image somewhere between your pole and your focus. Suppose this is the image. Parallel ray will pass through focus point. One ray will pass through center of curvature. They will meet. It will be inverted, but it will be always smaller than this object. Okay. But if you put your image at center of curvature, okay, because putting your image at focus will make the image at infinity, you know that. But what if we put our object at center of curvature? So parallel rays will pass through focus point, and and the other ray which will pass through the center of curvature, okay, and they will, so yeah, so they will meet somewhere, okay. mm, Wait, uh, okay, this ray diagram is problem. Should not be like this. Let's try to draw it again. So I'm not able to draw circle properly. Yeah, so this should be fine. This is a concave mirror. Here is your radius of curvature. Here is your focal point. Now what I'm saying is that suppose you have a object here, okay, parallel rays going like this, converging here at this point, okay, and then you can have a ray like going like this from the focal length, and what will happen is that it will become parallel, okay, and it will pass through this, so it will match here, so you will have your image inverted at C. Yeah, This is a good tree diagram. So you see, to have a same height object, you have to put your same height image as your object. You have to put your object as at center of curvature, and which is c equal to 2f, 2 times of focal length, and here focal length is given 10 centimeters, so 20 centimeter is the answer. So 20 centimeter in the front of the mirror. Yeah. So this way you can think about this. So this is the last problem that I have today. So thank you. See you next Saturday.